Hello all, very good evening. Let us get started. Right. So today we are going to discuss about multiple linear regression equation. So yesterday we have discussed about simple linear regression, and today we are going to discuss about multiple linear regression equation. Let us understand what is the difference between the simple linear regression and multiple linear regression. So before that, let me recap quickly what we have discussed yesterday. So because there is a relation between the simple linear and multiple linear regression equation. Linear regression equation, the generic form is y equal to beta naught plus beta 1 x plus epsilon naught. So in this y is dependent variable, beta naught is a y-intercept, beta 1 is a slope of the regression line, and x is a independent variable, and epsilon naught is the error. So this is a regression equation. And coming to simple linear regression, so if you have only one independent variable, then that is called as simple linear regression equation, that is this. And yesterday we have seen a couple of examples. Also, we have built a simple linear regression equation for an example of Sunday newspaper edition estimation using the daily newspaper editions. Right. So that's what we solved yesterday. And once you build the regression equation, so to find out the regression equation is a good regression equation or it is a mediocre regression equation using the R-square value. If R-square value is near to 1, then we can say that is a very good regression equation, and R-square value is less than, so 0.6 or 0.5, then that is not a good regression equation, and we have to find out various ways how we can improve the R-square value, right? Right. And then after that, we also discussed about the p-values. Okay, p-values for the variables. If the p-value is less than 0.05, okay, less than 0.05, then we can say the corresponding variable is significant and which will be useful for us in the regression equation. So if the value is more than 0.05, okay, then we can say that a variable or the independent variable is not really useful in predicting the dependent variable, or so that is not useful in the regression equation. So this is what we have discussed yesterday. Right? Now, today we are going to discuss about MLR, multiple linear regression equation. The difference here, the simple linear regression equation and multiple linear regression equation. So in this multiple linear regression equation, we are going to use multiple independent variables. So beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus so on so plus beta k xk. Meaning, so in the multiple linear regression equation, we are going to use multiple independent variables. Multiple independent variables, so based on the problem statement. So we are not going to limit the equation or the variable set to only one independent variable. So here we are going to consider multiple independent variables. So that is called as multiple linear regression equation. Okay. So these are the learning goals. Okay. Anyway, we are going to discuss that in detail. Yeah. Now let me give you one real life application of this multiple linear regression equation. Car wallet. Okay. Let me open this site. Right. So this is the car wallet website. So if you want to buy a used car or if you want to sell your used car, so you want to know the worth of the car, right? So what is the price, minimum price or maximum price that you can quote or that you can offer? So for that purpose, so generally, so what do we do? So we'll inquire the friends or mechanic, hey, how much we can offer for this, or how much I can quote to the potential buyers. So these suggestions will take from the people who are experienced in that field. Now let us see today. So how the multiple linear regression equation will be used to find out the price of a used car. So when I say multiple linear regression equation, not exactly, but similar kind of algorithm. So this website is using. Now let's say, for example, I have a car. So I want to sell this car. Okay, this is a used car. The manufacturing, the year is, let's say, 2019, month Jan, make. Okay, for example, Maruti Suzuki. Okay, model, let's say, design. and version, for example, let me select these things randomly. City, let's say Mumbai here, and number of owners, first owner, kilometers, okay, 50,000 kilometers, let's say. So these are the details of the car. Now these details so would act as a parameters, and the back end, the algorithm is going to run in the website, and then we'll get the price. You see, check values. Now we have a different variants. So in the markets which we desire, right? And fair car condition 5,71,000, and if it is a good car 6,13,000. Right? So VDI. So like that. So for different versions, you can get this the fair. If the car is in fair condition, if it is in good condition, this is the price range. How this is being estimated? So that is based on the algorithm. Now, so you can think of the regression equation here is like this. The price of the car equal to beta naught plus beta 1 to manufacture year month. So based on this, we can find out the age of the car, right? Beta 1 into age plus beta 2 into the make plus beta 3 into version. Okay. So plus beta 4 so into city. So like that, all the variables. So beta 4 into number of owners, beta 5 into owners, plus beta 6 into kilometers. So this is my regression equation. Now what we have done is just, so we have given these details, the parameter details, age, make, and all these things. And from the historical data, the beta naught, beta 1, beta 2 would be estimated. So we have seen this yesterday, how we can estimate these things, right? And based on the historical data, we can estimate these values. And then when you submit so these your car's information to the regression equation, based on this, I'll get these price values. So that is what actually, so this Carbala website has done. So this is a classical example of the multiple linear regression equation, right? Okay. So that means the real life problems okay, is not only limited to the simple linear regression equation, but we have to use multiple linear. That means wherein to solve a problem where we have to consider multiple parameters or multiple factors. So that is the idea here. Okay. Fine. So before building this multiple linear regression MLR, we have to have some assumptions. Okay, so these are the assumptions that we have to before assume before building the model, and also once you build the model, we have to validate whether these assumptions are complying or are there any violations to this assumption. So that we'll do after completion or after building the model. Well, first let us discuss about what are these assumptions are about. The first one is linearity. So linear in the parameters, what are the parameters that you are talking about? These parameters have to be linear and not the exponents or some other form. Okay, so that is first assumption. The second assumption about the errors, and this is very important, and we are going to spend good amount of time on these assumptions about the errors. Okay, first one is, first let us understand what are the errors first of all. Errors, how do you find out errors? So errors are nothing but, so yi minus yi hat. What is yi? The actual values in the dependent variable. Yi hat, so this is the predicted value from a regression equation. So from regression equation, right? So that is what the difference between these two values is called as error. Now we are talking about these errors. So errors should be IID. So independently and identically distributed. So once you build the regression equation like this, then you compute this error. Then when you collect all the errors should be independently and identically distributed. So that is what IID. Then how do we check this? Yes, so we have methods to check this. And zero mean. So when you compute the mean for the errors across all the data points, the mean should be 0. Then the constant variance. So this is also called as homoscedasticity. So when you get these errors, and when you plot, okay, so the plot should not show any patterns. So it should be randomly distributed across the plot. The that is what actually called as homoscedasticity, and independent of each other. The data point, the errors should not depend on any. So the previous data points are later data points. So that is what the independent of each other. So these things we are going to evaluate after completion of the model. And these are the other assumption, but most importantly, so we are going to validate these errors. Okay. So now we are going to understand this multiple linear regression equation using an example. Okay. So this is a example or business case we are going to discuss cars. What we want to do is, so I want to build a MLR, multiple linear regression algorithm, that predicts the mileage. Okay, the mileage, okay, MPG in short, that is miles, average miles per gallon. That is nothing but mileage. So I want to find out the mileage given these parameters of a car. Volume, the volume is nothing but cubic feet of cab space. HP, engine horsepower. SP, top speed, okay, miles per hour. WT, vehicle weight. Okay, so this, based on these parameters, yeah, so we want to find out the vehicle miles per gallon. That is what our objective is. Now my regression equation looks like. So MPG, miles per gallon, this is a y variable, is equal to beta naught plus beta 1 into volume plus beta 2 into HP plus beta 3 into SP plus beta 4 into WT. Right? So this is my regression equation. What I want to do, let's say I have a car. So this car has certain the volume, the cubic, the feet of cap space. HP, this car will have certain HP horsepower, the engine horsepower, top speed, then weight of this vehicle. So once I know all this information, simply I want to plug into this equation, then I can get to know the miles per gallon for this car. So that is what I want to find out. Now, before that, in this equation, what we do not know? We do not know beta naught, we do not know beta 1, beta 2, beta 3, beta 4. Right? So these parameters I do not know. I know this volume. From where you will get this volume? You know the car's volume, right? So which car you want to find out MPG, that car's volume. So you'll put into this. So in this equation, I don't know beta naught, beta 1, these betas I don't know. From where we'll get those betas? We will estimate using OLS, ordinary least squares method. Yesterday we discussed, right? The least squares method or OLS, ordinary least squares method. Using this, we are going to estimate from the data. I have a data set for this. From this data set, we are going to estimate this beta naught, beta 1, beta 2, all these things. Once I know beta naught, beta 1, all these things, simply I can plug the car's volume, HP, SP, and weight. Then my regression equation is ready, and I can predict for a new car. So that is the idea here. Okay. All right. Now let me show you the data set. Yeah, this is a data set. Okay. So in this data set, as we discussed, we have variables. So this is my dependent variable and HP, volume, SP, and weight. These are the independent variables, right? And so based on this data, we are going to apply OLS, the regression analysis, and then we'll get to know the beta naught, beta 1 and all those things. Then we'll plug into our equation. So that is the idea. Okay, fine. So the first step, so in building the regression equation, is to analyze the data. So analyze and generate insights, and based on that insights, so we can understand the data set, right? So as part of that, the data analysis, we have applied the scatter plot as we discussed yesterday, and also the correlation coefficient. So what scatter plot does, it gives us the visual representation of the data, what kind of association the variables shares, right? And here the correlation coefficient gives us the strength of association. So how strong that relationship between the two variables. So that is what we want to find out. Now, so this is the scatter plot and correlation coefficient. Then how do we understand, how do we interpret this? Let us say I want to find out this plot. You see, this is a scatter plot. This plot is between two variables. But which are those two variables? To understand that, what you can do is you can draw a line from here to here, or other way around. So I'll come back like this. So I want to find out the plot, the scatter plot between the MPG versus SP. Simply, so I can draw a line from MPG, and I can draw a line from SP. So where these two lines intersect, so this is the diagram that is between MPG versus SP, the scatter plot. Okay. Like this. For example, I want to find out volume versus HP. Simply draw a line like this, draw a line like this, and these two lines intersect here. So this is the line, scatter plot that is between HP versus volume. So that's how so we can understand the plot, okay, between the two variables. Okay. Now let us generate some interesting insights. The interesting insights I meant, so which are the variables have high correlation with positive or negative? With positive or negative, sorry. Or which are the variables have the association, so that is not a significant association, right? For example, if you see here, this. So this is scatter plot between HP versus MPG, right? And what kind of association do you see here? The association is negative, that is evident here, it is going down. So this is one insight. And how much is the strength of this association? Negative 0.73. So this is the strength of the association, which is nothing but the correlation coefficient small r. Then this is, so this is slightly positive, and this is slightly negative. This is positive, HP versus SP, right? And this is negative, slightly positive, slightly negative, slightly positive, a highly positive between volume and weight. So because if you see this, so this one, the correlation coefficient, how much it is? Positive one, perfect one between volume and weight, right? And SP versus weight, this is positive, slightly positive. Okay. So this is fine. We have understood the relationship between the various parameters. But most important, the association that we need to understand here is the dependent variable versus all other independent variables. So how is the association? So between MPG versus HP, that is negative 1. MPG versus volume, this also negative. MPG versus SP, this also negative. MPG versus weight, this also negative, right? So yeah, that means MPG is sharing the negative association across the variables. Meaning, if I increase a car's horsepower or volume of a car, top speed of a car, weight of a car, my MPG, the mileage is going down. Now let us wear a hat of the domain expert from the automotive domain. Do you agree this fact that if I increase volume or top speed of a car, weight of a car, HP of a car, does the MPG goes down? Yes, of course. So for a high-end car, let's say for example, you have a bigger car, definitely the miles per gallon, the mileage definitely will be lower in comparison to the other cars where the weight is not that much high. Even the horsepower, if the horsepower is high, the high-end cars, sports cars, for example, okay, our top speed, where the car's top speed is very high, so 200 kilometers per hour, 250 kilometers per hour, this kind of a top speed cars, definitely the MPG would be, the mileage will be low only. The weight of a car is more, the mileage would be low. That means, yes, whatever the data that so shows here, so that confirms our understanding about the vehicles. This is very, very important. So you have to confirm your knowledge, or you have to verify the data that is correct or not. Let's say, for example, so you have got the HP versus MPG. The plot is like this. Let me try. So this is HP, so MPG and HP. This is what actually I've got it. What kind of association is positive association like this? That means as HP increases, so MPG also increases. So now this has to be validated by the domain experts. So in domain, in the vehicle, is it so? No, this is wrong. It doesn't happen in the vehicles, right? Because as HP increases, the MPG has to go down. It doesn't increase. If you happen to see this kind of association, so there are two possibilities. One is the data is not correct. Data is wrong. Second thing is your domain knowledge is not correct. That means you have to confirm whether so this can happen in any of the cases. So probably there are special cars where HP increases, the mileage also increases. That means whatever the domain that you have, that has to be corrected. So this is very, very, very important when you are building a model. You have to analyze the data, you have to generate the insights and validate the data whether the data is correct, or you have to get your domain knowledge verified and corrected. Okay, yes, fine. Now let us go ahead and build the model. So model building is again the straightforward single command you can use to build the model, and these are the model. This is the model output. So I have the volume. Okay. This is the coefficient of volume. What is the coefficient of volume? If you see the model building, MPG equal to beta naught. What is the beta naught? 30.67 plus beta 1 volume, okay, plus beta 2 HP beta 4 weight. Okay. So this is my equation. Now what is the coefficient of volume? Beta 1. So that means this value is beta 1. You see coefficient of volume beta 1, coefficient of HP beta 2, beta 3, beta 4. Simply I'll take these values, I'll plug into these betas, and I'll take this intercept, I'll put it here. Then my regression equation is ready. All right. So this is ready. Now, as we discussed yesterday, there are a few things that we have to check before we use this regression equation. First thing is multiple R square. This one. So R square value. So how much it is? 0.77. So if it is more than 0.6 or 0.65, yes, of course, that is okay, kind of a good equation. This is a good equation, 0.77, right? And now coming to the p values. What are these p values for? So p values are to find out the variable is significant, or the variable is useful for us to predict the y variable, or that is not going to be useful for us. So that is where we will use this p value. So how do we interpret? So if the p value is less than 0.05, then we'll say so that variable is not useful for us. If this is, let's say for example, if the p value is less than 0.05, then that variable is useful for us. If the p value is more than 0.5, then that variable is not going to be useful for us. Okay. Now let us check this. So anyway, intercept. So we don't have to check that. Even though this is more than or less than, still you have to use it. The second one is here is volume. Is volume significant? No. This is more than 0.05. This is not significant. This one, yes. So this value, you see, E, any value, let's say for example 1.2 E minus 0.6. What is this E? So this is a scientific way of writing the decimal values. So this is equivalent to 1.2 into 10 power minus 6. E minus 6 means 10 power minus 6. So this is almost 0, right? Similarly here also 1.4 E minus 6 means this is almost 0. So which is less than 0.05. And this one which is less than 0.05, which is greater than 0.9. Now out of all these things, so this variable volume is not significant and weight is also not significant, and leftover variables are these. So HP and HP. Now my regression equation would become like this. So MPG is equal to beta naught plus beta 1 into no volume. This is HP plus beta 2 into SP. Right. So this is my regression equation. Right. So that's how you can build the regression equation and you can evaluate the regression equation based on this. Okay. Now, the key question here is, so whatever we had discussed, okay, so everything seems fine to you, or is there any flaw that we have discussed? Is there any the mistake whatever we have discussed so far? What do you think? Is there any mistake or is there any flaw in our discussion whatever we had so far, especially in the output of regression here? See, we are saying that volume and weight is not significant, meaning the volume and weight is not going to have any effect in deciding mileage. Is it so? Do you agree if I say that, hey, no matter what, so how big is your cab space, how much weight your vehicle has, it doesn't have any effect on MPG. If I say this statement, would you agree? So would you agree if I say that? Right. So you don't agree, right? Even so, if we say that, hey, I have built a regression equation and this is my regression equation, and I know the volume and weight, so it doesn't have any effect on MPG. So if you say to the engineers, the mechanical engineers or the domain experts, simply they'll throw your regression equation in the dustbin, right? Because they know that volume and weight plays a crucial role in deciding the MPG along with these parameters. And if you say that, hey, this is my regression equation, so you cannot say that these are going to show have an effect on the MPG. No, don't believe the regression output just blindly like this. Okay? That means, so whatever the regression equation that we have generated, yes, so far this is correct, but so this has to be evaluated further. So those evaluation steps we are going to discuss now. That means whatever we have got, so there's some mistake, some flaws there in this regression equation. Now let us see what is that mistake in this regression equation. Right. So this p-value, right? So this p-value we have got from the hypothesis test. Okay, if you have attended this lecture on hypothesis test, we have discussed a detailed discussion we had. Based on this hypothesis test, so we will compute the t-value. Then based on the t-value, so we have computed the p-value. These p-values are coming from this hypothesis test. Right. Now, so we have realized that the volume and weight, so these also have to play a crucial role, but so somehow the regression equation found that the volume is not significant and also weight not significant. Now let us do one thing. Let us do one experiment. What we are going to do is, so instead of considering all these variables, I'll take only the volume. Okay? And then I'll build a simple linear regression equation on MPG. That means I'm going to build MPG is equal to beta naught plus beta 1 into volume This is one equation I will build. And then one more equation also I'm going to build. MPG is equal to beta naught plus beta 1 into weight. That means, so I'm going to take this variable alone. I'll build simple linear regression equation the way yesterday how we have built in similar manner. And also I'll take this variable again and I'm going to build a second equation. Let us see in those equations whether the volume would become significant and here also weight would become significant. Then let us evaluate that. Yes, here is a regression equation. First equation MPG on volume. MPG is equal to beta naught plus beta 1 to volume. And tell me, do we have a significance here? So just volume alone we have used to build the regression equation. Yes, this is highly significant, very high significance, right? And so this also MPG on weight. So this also high significant. So highly significant variable. This is almost 0, here also almost 0, right? Meaning individually when you use volume, so it is significant, weight, it is significant. Fine, there is no problem with the volume and weight, and there is no problem with the regression equation also, right? Now let us do one more experiment. Let us combine these two variables. Let us build multiple linear regression equation. MPG equal to beta naught plus beta 1 volume plus beta 2 weight. So let us build this regression equation. Let us see. So the significance levels of these two variables. Okay. Yes. So this is the regression equation with weight and volume. Okay. Now what do you observe here? What is the p-value here? Which is more than 0.05. What is the p-value for this weight? Is also more than 0.05. So that means, so when you use this volume alone in a regression equation, so that is that became significant. When you use weight alone in regression equation, that also became significant. But when you combine the volume and weight together, they are insignificant. Meaning there is something wrong between these two variables. So that problem is called as collinearity. Multicollinearity or collinearity. What is a collinearity? Let us discuss now. So if you observe, so scatter plot and correlation coefficient. Okay. So between volume and weight, these two are the problematic variables, right? Now let us see what is the correlation between these two. Perfect correlation, positive correlation, perfect one. That means in any of the independent variables, okay, any of the independent variables x1, x2, x3, so and so, if the correlation is perfect 1 or -1, okay, any of this, so I, j. So if it is positive 1 or if it is negative 1, so these variables, independent variables, would create a problem called collinearity or multicollinearity. Okay. So the ill effect of the collinearity or multicollinearity is, so ill effect of this collinearity or multicollinearity is the variables which supposed to be significant would become insignificant. So because of this multicollinearity problem, right? Then how to detect this multicollinearity? In this case, we have done several experiments. We have built multiple algorithms. Then we found out that there is a problem of multicollinearity. But in general case, so would you do all these things? No, right? So how do you detect this multicollinearity? So that is using a methodology called variance inflation factor or VIF. In short, these are called as VIF. So VIF, so formula for the VIF is this. So 1 by 1 minus R square J. Okay, so this is a formula we are going to use. So when you use this formula, we will get a score, a numerical value for all the variables in the data set, volume, HP, and SP weight. So this is a this is a value, the score that we'll get for each and every variable in the data set. Then how do we interpret this? The interpretation goes like this. If the value is more than 20. Roughly, so it's not a strict, no, the definition. Roughly, if it is more than 20, then you can say the variables are involved in the multi-collinearity problem. Now you see here for volume, which is more than 20, and for weight, which is more than 20. So that means these two variables are involved in the multi-collinearity problem. So there are some textbooks. Okay. So they also suggest if it is value is more than 10, then you can suspect. You can say that the variables are in multi-collinearity, but majority of the times we'll go by this number. Yeah. Now, how do we get this value? Yeah, how do we get that value? Right, the value will get like this. So VAF of 1 by 1 minus R square J, right? So this is the formula. Now let us see how do we get this 638 for this volume. That is what we are going to discuss now. I want to find out the VAF value of volume. So that is equal to 1 by 1 minus R square of volume. How do I get R square value for a volume? So R square value for a volume I'll get. So when I build a regression equation, right? So when I build a regression equation by treating volume as a y variable, treat volume as a y variable, build a regression equation on the rest of the independent variables. Meaning, so build a regression equation beta naught, beta 1 HP plus beta 2 SP plus beta 3 W. Right? So build a regression equation by treating volume as a y variable. Then here I'll get a R square, right? So this R square value belongs to volume, and take that R square value and plug into this equation. Then I'll get a score. That score is 638.80. So like that. So for this also, treat HP as a y variable, build a regression equation on all other variables, then get a R square value for HP, then plug into this. Then you'll get so 19.92. That is what. So this is actually you can get the score for the VIF, variance inflation factor. Okay. Then based on that, we can identify whether so there is a the problem of the multi-collinearity or not. Okay. And then from the correlation matrix also, we can suspect whether the multi-collinearity problem is there in the data set or not. So if the correlation value is very, very high, almost positive one or almost negative one, then you can suspect. Here you see volume and weight, this is one, right? Even you can see HP versus SP. So this also very high correlation, but this is not exactly one, this is 0.97. Right. So based on this, we can suspect that yeah, there might be a multi-collinearity problem, and you can confirm using this VIF, variance inflation factor. So that's how we can detect the problem of VIF. Okay. So once you identify the problem of the multi-collinearity, then how do we remove that problem? Okay. So how do we remove the problem of multi-collinearity? Simple logic here is, see, we identified that weight and volume, these two are involved in the multi-collinearity problem. Then what we can do is simply discard one of the variables, right? Then the problem is resolved. You see here, this is a subset of variable. I have removed just weight, volume, HP, SP. These are the three variables. When I build the regression equation, now you see volume, the significance level very high. This is almost 0. And even if I remove volume, if I build the regression equation with weight, then also the weight is highly significant. That means we should not combine the weight and volume. Just ignore or discard one of these variables. That is a solution. That means go for subset of the variables. Do not include all the variables. What are the variables that are involved in the multi-collinearity problem? Discard one of the variables. That is simple solution of the multi-collinearity problem. So that is called as subset selection. Subset selection. So what do you mean by subset selection? Out of all the variables, HP, SP, volume, and weight, out of all these variables, select subset, and that subset will not have the problem of multi-collinearity. Okay. Based on R square value and based on AAC value. Right? So based on these two values, we are going to select the subset, and that subset, the feature subset, will not have the problem of multicollinearity. Right. So what we are going to do is we are going to build a regression equation MPG with respect to HP or this. So HP plus SP plus volume plus weight. Then for this regression equation, so I'll compute R square value I'll get, and also I'll get the AAC value. So what is AAC? So AAC stands for archaic information criteria. So this is AIC. So how do you compute? So this is a formula to compute the AAC value. And for a given model, if AAC value is low, then that model is a good model. Good model, right? So that is the interpretation. So the intuition behind this is a simple model is a good model. If you have large number of parameters in the data set and lesser number of data points, then that is not a good model. Wherein you should have lesser number of parameters, okay, and large number of data points. So that's where actually, okay, so you have the low AAC value, then that is a good model. That's the intuition behind this AAC value, right? So first model. Then second model, what we do is MPG, remove one variable. This variable has been removed. Then again keep track of R square AAC value. Then repeat this for all the combination. Remove one of the variables, find out R square value, AAC value. Then so repeat this multiple combinations for which combination the R square value is high, AAC value is low. That combination is a best combination, does not have the problem of multicollinearity. So that's how so we can identify the best parameters or best combination or the subset of the features, so that will not have the problem of multicollinearity, right? Great. Hope this is clear to you. Great. Now, so just pay attention here. So this is a very important slide, the flow of the model building process we are going to discuss. So let me give you the overall picture, the holistic view of the model building process, right? And then so you can think where we have, where we are, what we have discussed, and what we have to discuss yet. That will be clear to you. This is my data set. You can think of this is a cast data set that we are using. We have column rows, okay, number of different rows, and we have six or five columns we have. So once we have the data set, so what we have done EDA. That means the scatter plot, correlation, and all those things we have done. So that is basically called as exploratory data analysis or data analysis. Okay, and with this we have gotten certain understanding of the data set, right? So after that we have built the model, multiple linear regression analysis, okay, MLR we have built. After that, what we have to do, we have to validate, validation. Model validation. So as part of model validation, already we have done one part, that is multicollinearity. So this we have checked already. Then we are going to discuss a few more things as part of this model validation technique that we'll discuss. Okay. And then after that, deletion diagnostics. So deletion diagnostics. Okay. So here also we are going to discuss a bunch of techniques here. Then this deletion diagnostics is all about identifying the outliers in the data set, identifying influential data points in the data set, and remove those data points. That means, so we are going back to the data set. Outliers, influencers. Okay. So these outliers and influencers so would be removed from this data set and again goes through this entire process. Then build the model, then validation techniques, then again deletion diagnostics. And this loop, this process continues until you don't find any outliers or influencers. So once you are fine with that, then so we'll go for the model deployment or prediction. So this model will finalize. This model will use for the so prediction purpose. So in the production environment, right? Now these are the different phases of the model building process. So now we have the data set we have discussed, EDA, scatter plot, and correlation we have discussed, and we have discussed with the model output. And now we are in the phase of model validation. Okay, model validation. So as part of this model validation, we have discussed this multi-collinearity. Okay, so this problem we've discussed. Then also we have discussed how to counter the problem using the subset selection of the features. Then we are going to discuss a few more techniques as part of the model validation. Those are this. Okay. So these three more techniques we are going to discuss as part of model validation. Then we will move to the deletion diagnostics. Then we'll solve the problems. Then final model will get it. Right? Okay. So this is a process. Yeah. So now let us take a break. A 10 minutes break. Now it is how much? What is the time now? Yeah, 6:52. So a 10 minutes break we'll take. After that, we'll continue discussion on the model validation. So at 7:02, we'll start. Yeah, hello all. Let's continue the discussion. Right. So before the break, we were discussing about the model building process, right? So the data, okay, EDA, MLR, right? So the model validation. So we have discussed as part of this model validation the multi-collinearity problem. Then now let us discuss a few more validation methods, right? And as part of this model validation, we are also going to verify whether the assumptions that we made about the errors before building the model holds good, or are there any violations about the error, the assumptions about the errors. So that is what we are going to verify as part of this validation, right? So the residuals are the errors, right? So how do we compute these errors? So EI, that error is nothing but the difference between the actual value and the predicted value, right? So that is the error. Now we are going to plot the visualizations between the errors versus yi cap. That is, I'll connect the error here. For example, I have x, this is my y. You can think of this is probably the experience and this is salary. And then I'll build a regression equation. Okay. And this using the regression equation, I can get the yi hat. And then the difference between y minus yi hat, that is nothing but the error. That is what we are discussing, yi minus yi hat. Right? Okay. So then we are talking about the plot between the error versus yi hat or yi cap. So I'll take the values of error and I'll take the values of predicted values, then I'll plot it. So this is my yi hat and this is error, standardized error, something like that we'll use. And then we'll have the data points here. Then how do we interpret the plot here? Let's say the plot values are like this. Like this we have. Okay. So we'll discuss how to interpret this plot and different symbol, different shapes or patterns. All those things we'll discuss in the next slide. Okay. So this is one plot. The second plot, EI versus XI. So I have variable also, right? So this is one variable. So I'm going to plot the visualizations between this variable or this data and the error data. So if you have multiple variables, so let's say this is x5, okay, this is x4, x3. If at all, if you have multiple variables, I'll take all of them, I'll plot one by one. So one plot is for, so EI versus x1. The other plot, EI versus x2. So like that, so I'll take all these independent variables, I'll plot one by one, right? So that's how we are going to see. And based on the pattern and based on the data, how the data is, we are going to take the decisions. The third one is QQ plot. This QQ plot is all about how the error data is distributed, whether the errors are following normal distribution or not. That will check using this QQ plot. So as part of this model validation techniques, we are going to discuss about a plot EI versus YI hat, EA versus XI, and the QQ plot. Now let us see the first plot. So fitted versus residual R. So this also called as YI hat and this is EI, standardized EI. And what to look for? How do we interpret this? No pattern, no problems. What do you mean by pattern? So in this plot, okay, if you see, for example, this kind of thing. So what is happening here? So first, actually, the error is reducing. Then after that, error is increasing. That means there is a pattern, right? Decreasing, then increasing. So if you see this kind of a pattern or any other pattern like this, increasing and decreasing, or if the data points are clustered, okay, like this. So at one place many data points are there like this, or here we have many data points. So if you see any kind of thing, so a pattern increasing, decreasing, clusters, mixtures, and all these things are considered as a pattern. If you see this kind of pattern, that means your model is not good model, because your errors contains good amount of information. So because of that information only, the patterns are visible here. So how the plot looks like if there are no patterns at all. So if the data is like this, the data is like this. Do you see any pattern here? No, all the data points are randomly scattered here across the plot. There is no pattern, there is no up and downs, or there is no clusters, mixtures. If you compare this, so this plot is a good plot. If you have to say your model is a good model, right? So that means no patterns, no problems. If you see any pattern like this, that model is not good model. If you see the data is randomly distributed across the plot, then that is a good for the model. That means your model is a good model. Now coming to our model, this is a cost dataset model, cost dataset. You see here, so the data starts here and it is going down little bit, okay, little bit. Then again after that it is going up. So based on the density of the data point, just approximately I have drawn this line. And also, so this is where actually most of the data points are focused. That means there is something wrong with the model or something wrong with the data. So that's what actually we can interpret. That means based on this plot, if you don't find any pattern, then so that model is a good model. If you find increasing, decreasing, increasing like this, then you can say that model is not a good model. Then you have to find out the problems and you have to apply the corrective actions for that. So that is what it indicates. So make a note of that. Using this plot, we found some patterns and this is not so flat. So if this line is exactly horizontal to x-axis like this, then you can say there are no patterns. But here it is going down then going up. That means yes, there are certain patterns and we have to make a note of this and we'll see so how best we can solve this problem. Then the second one is QQ plot. QQ means quantile plot. Quantile plot. Right. So this is QQ plot. So the objective of this QQ plot is to check normality, whether the errors, so errors are following normal distribution or not, right? So how do we understand so the errors are following normal distribution or not? You see this solid red line. So if the data points, these data points are nothing but the errors, so exactly aligns on this solid red line, then you can say the errors are following normal distribution. If exactly it aligns on the red line, then we can say. So, or at least if the data points are between these dotted lines, the data points are between these dotted lines, you see here. So then you can say with 95% confidence, the data points are following normal distribution. You can see some of the data points are within these dotted lines. These are nothing but the confidence intervals that we have discussed, right? Confidence intervals, and these data points are violating that assumption, that normality here also, and this data point is very far away from these limits, right? So that means there are certain violations, but major of the data points are so within these dotted lines. That means with a 95% confidence, the errors are following normal distribution with certain violations. So here 77 are okay, so 71 little bit. So these things are, so we have to take care, right? So this is to check whether errors are following normal distributions or not. Okay. Then a regressor versus a residual, that is xi versus error. Okay. This is the third plot that we discussed. So this plot, so this is the main plot that we have to analyze. So how do we interpret this? The interpretation is same. No pattern, No worries, no problem. Okay. So no patterns, no problems. So if you see any patterns like so going up, going down up, or certain places, if you see more data points, then you can say that model is not good model, or the variable that you're talking about. So this needs transformations. So transformations, what kind of transformations? You can go for square transformation, square root transformation, log transformation, okay, log x, or log of 1 by square root of x. So all these kind of transformations you can think of, right? So if there are certain patterns in the plot here, okay, so that is one thing. And these are the other plots where so we can understand the importance of the volume or the variable. So whether this variable is important really. So if so, you will see the slope. You see this is called as CCPR, component and component plus residual plot. So if you see the slope is very high, then the variable is very important. The higher the slope, the better the variable. If the slope is not there, and if the slope is like this, for example, zero slope, then the variable so is not important. So based on that, we can understand whether the variable is important or not. So in these two plots, out of all these, the important plots are, so this is one plot and this another plot. So based on this, we can understand whether the variable is a good variable or variable needs some kind of transformation. So based on this plot. Okay. So now what we have discussed. Let me go back to the floor here. So we have discussed model validation. As part of model validation, we discussed about multicollinearity and we discussed about QQ plot. Excuse me. We discussed about errors, errors versus yi hat plot, and we discussed about errors versus xi. So these three plots we have discussed. So the QQ plot is to check for the normality, and these two plots to check whether are there any patterns in the plot, and that gives us an indication for the necessary transformation of the data. Right. So this is for the this is all about the model validation techniques. Right. Now we are going to discuss about model deletion diagnostics. Let us see the model deletion diagnostics now. Right. So as part of model deletion diagnostics, so we are going to discuss about a few techniques again. So one is Cook's distance. And then we are going to discuss about leverage. So leverage points or hat points. So these are the two things we are going to discuss as part of this model deletion diagnostics. Okay. Now let us understand. So what do you mean by deletion diagnostics? What is a deletion diagnostics? That means we are going to delete the data points based on these diagnostics, right? So we are going to connect some diagnostics on the model, and then we identify the data points that have to be deleted, and we'll delete the data and we'll build the model. Then we again, so that continues the loop then until we don't find any problems with the model. That is what actually deletion diagnostics are about. Now, let me give you a scenario here. I have a data set. And I have data points like this. Okay, so these are data set one. And with this, if I build the regression equation, so I might get the regression equation like this. So these are a regression equation one, data for data set one. Now what I've done is just I've removed so these two data points, and I've kept all the data points as it is. Okay. Right. So this everything I have replicated here. This is data set two. So just I have removed these two data points. So with this, so I have built a regression equation like this. This is my regression equation 2. Now, if I ask you a question, so which regression equation is a good regression equation? Data set 1 or with data set 2? Exactly, right? So this is what actually is a good regression equation. But why? Because this regression line is going through middle of the data point, which is very near to all the data points. And you can say this is a representative of all the data points. But where in this? So this is not going through the middle of the data points, and it is not near to, so this data point, that is a majority of the data points. So because of these two data points in the data set, these two data points are pulling the regression line towards themselves, and in maintaining the lowest error, so this regression line has to move towards them also, right? So because of only two data points, so this regression line slope has been increased. So when you say, so the slope means, so if it is more towards the y-axis, then slope is increasing. If it is more towards the x-axis, then slope is decreasing. That is what the idea of the slope, right? Now you see, so this line is more near to the here y-axis comparison to this line. That means the slope is more here, more slope, higher slope. The slope is low here. In the absence of these data points, so this line settled down with these data points, and now this is a very good regression equation. Right? So when you say a regression equation, yeah, when you say a regression equation is a representative of the data points, then the regression equation should so be within this middle of the data points. Then I can say this is a right regression equation. But wherein here, because of the OLS, it has to maintain the minimum error. In doing so, even this line also has to be near to these two data points also. That means these two data points are pulling the regression equation aligned towards themselves, which is not fair, which is not right. Correct, right? So in this case, what we have to do is we have to identify these two data points and remove these two data points. And these two data points are considered as influencers or outliers. So if you remove these data points, then your regression equation would become like this. Now this line is a pretty much a good regression line, which is in between of the majority of the data points. Now this line represents my data points. Okay. Now using the Cook's distance, I'm going to find out these kind of outliers, and using leverage, I'm going to identify those influencer data points. Now let me give you the idea of how are you going to identify. Let's say we have 100 data points. These 100 data points. With these 100 data points, I have built the regression equation. I've got the values like this. So beta naught value, let's say 20. Beta 1 value, let us say 40. Okay. Beta 2, let us say this is so 37. So these are the scenario of the 100 data points. Now what we do is, this is a regression equation 1, for example. So I have removed one data point. With the remaining 99 data points, I have built a regression equation 2. And with that, the values are beta naught is 19.75, beta 1 41.02, beta 2 so 37 so 0.05, right? So then again what I've done is, so I have included the data point that I have removed from here, and I have removed a different data point. Okay, so I've removed a different data point. I included the data point that I have removed here. So with that, I've built one more regression equation. Now the beta naught is, let's say for example 10, beta 1 so is 1.2, beta 2, let's say that is so 2.75. So this is the scenario. So three regression equations that we have built, and these are the beta values. What do you observe? Do you see any strange that has happened here? Yes. So here in this case, regression equation 3, the beta values are completely different than than regression equation 1, regression equation 2. right? So why it is so? Because so when you build this regression equation, the data point that you have removed, one of the data points that you have removed this. So because of one data point that has been removed, so the line is slowly coming down, slowly coming down. So that means, so when you remove this a data point, if you see a drastic change in the betas like this, that means you have removed an outlier or influencer. In other words, one data point, so that is deciding the slope of your regression equation. But that should not be the case. The regression equation slope has to be decided collectively by all the data points, not because of one or two data points. Now, so one data point, the data point that you have removed, that decided how much the slope of the regression line should be, right? And when you remove that, so the regression equation slope, so that is settled down in this, and collectively all these data points have decided so the slope of the regression equation. Now in this case, we have removed this data point, that is influencer, and so based on that, so we are going to remove from the data set. That means the Cook's distance will help us so to detect which data point when you remove, there is a drastic change in the betas. The Cook's distance will give us, if you remove one data point, then when we will compare with the full data, the regression beta values with the subset of the regression beta values, then we, if the distance, so 40 minus 1.2, if the distance is huge, then we'll get that the Cook's distance value. And so this distance would be normalized with some other value. And if this is more than or equal to 1, if Cook's distance is more than or equal to 1, then we'll say that, hey, that is an influential data point or the outlier. Then we'll remove that outlier from the data set. So that is the idea of the Cook's distance. Okay. Right. So this is the Cook's distance. That means, so we have built a regression equation with all the data points, and then regression equation is a subset of by removing one data point at a time. And you see this one, 76. 76. If I remove 76 data point and build the regression equation, I have got beta naught, beta 1, beta 2 values. Then I've compared these beta values with this regression equation beta values with the full data set. Then the distance, the difference is more. That difference is, if it is more than or equal to 1, then that is called as influencers or outlier, right? So in this case, this is more than 1, and I can say that, yeah, so this is outlier. 76 data point is outlier. And other data points, so 0.2 and this is a 0.1 or something like that. Now let us focus on this. So what we do? So this we will remove from the data and we'll check again. We'll check again so that if you have any outliers in the data set again and again, that will be. One more thing is high influence point or the leverage. So this also gives us the idea of the influencer data points. And so we will compute a cutoff, a threshold value for the leverage. So using this 3 into k plus 1 by n, and k is number of features, dimensions in the data set, and n is number of data points. So if at all, if this value, okay, crossed by this leverage, then we'll say those are outliers or influential data points. For example, if my threshold value is like this, then I'll say data point 70th and 76th. So these are the influential data points we'll remove from the data set. And we have checked actually 70th data point and 76th data points are so the outliers, and these data points will remove from the data set, and then we'll build the model again, then we'll see the accuracy. Yeah. So that is the complete model building process. So if you go back to the model building process here that we have put together, we have discussed here, and as part of the model deletion diagnostics, we discussed about Cook's distance, and we discussed about the leverage points. Based on that, so we have removed 70th and 76th data points. Then we'll go back to the, remove these two data points and build the model again and check. And again, so this loop continues until you don't find any problems with the model. Then that is the final model, you will get it. Okay. So this is the model building process completely. Okay. Now let me show you the Python coding. Yeah, let me show you the Python coding. Then, yeah, so you will understand and how you can build and how you can go through all this the process. All right. So now let us see so how we can implement this multiple linear regression equation in Python. So what are the steps that we have seen? So all those steps we are going to see in Python now. And here are the libraries. So this is Cborn. Cborn is for the visualization, and this is a matplotlib. Okay, so this is also for visualization, and this is stats model. Okay, this is basically to build a model as well as to generate the Cook's distance plots. Right? And the pandas and numpy, these are for generic data processing libraries. Let me execute this one by one. And then read the data set. So this is my data set. We have HP, MPG, volume, right? And SP, weight. Then generate the cost information. And find out if you have any NA values in the data set, missing values in the data set. Then correlation matrix. Yeah, so you can see this correlation matrix like the correlation between HP versus MPG, volume versus all these things you can analyze. As we discussed, you can go through that. Now let us generate the pair plots. The pair plots are nothing but the histograms and the scatter plots. So combination of histogram and scatter plots, we'll get it here. Right. So here you can see. So HP variable histogram, and this is HP versus this one, MPG versus HP. Yeah, this plot, scatter plot is between MPG versus HP, and this is volume versus HP. So like that, the scatter plot as well as the histograms on the diagonal boxes. Then build the model. Okay, stats model.formula API, as we discussed yesterday, this is a Y variable, and all the independent variables. So just you have to join with the plus symbol and fit the model. Then these are the model parameters, right? So weight, volume, and all these things. Then you can see the p values and model the t values. So these are the first one is these are the t values. So here you can see the first command. The second command is model p values. So these are the p values. Then as we discussed for the weight and volume, the p values are more than 0.05. So that's where actually we discussed about the multi-collinearity problem. And also the model R square value 77. Okay. And then now we have done the experiment, right? So MPG with volume alone, MPG with weight alone. Then we combined MPG weight and volume. All these things. Let us do this. Yeah. Now computing the VIF, right? So the same formula just we have written here. So first to build the regression equation with HP, then you will get the VIF for the HP. Then like that you can build for all other variables by treating them as Y variable. Then you will get the VIF values. So for HP, WT, volume, and SP, you can see this. Then this is a residual analysis. Okay. So test for normality, that is a QQ plot. So yeah, this is a QQ plot, and these are the data points which are very far away from this rest of the data points on this line also. Then I want to find out what are the index values of these two data points which are very far away from the solid red line. So for that, just I want to I'll use this np.where method. Model residual. These are the model residual where the values are more than 10. You see here 10, more than 10. Just list out those indexes. So that is 0th index and 76th index. These two are these data points. Okay, make a note of that. We will also see whether these are becoming the outliers and influences the Cook's plot. A residual plot for homoscedasticity. So this is basically the plot between the fitted values versus standardized errors. This is what actually we have seen in the presentation, and this is going down and then it is going up a little. The pattern is visible here. Fine. Then residual versus regressor. So this is also the plot that we have seen. The residual means independent variable versus the errors, right? So this is a plot and this is a CCPR plot. So like that for each and every variable, we have to generate this for all the 4 variables. All right. So then we are going to discuss about the model deletion diagnostics. Okay. So using Cook's distance, okay, generate the Cook's distance and the plot of the Cook's distance. So you can see here. So this is what we discussed. 76 or some index value we'll find out. Okay, so the value of the Cook's distance is more than 1. Okay. Then so let us find out. So the highest value, the index 76th, the data point is 76th data point. The value is 1.08, and the 76 also came up. So if you recall our discussion here, we're in the QQ plot, right? Right. You see here QQ plot also 76th data point. So came up. That means 76th data point is really an outlier or influencer that we can understand. Minimize this. Yeah. Right. So then we'll make a note of that. The 76th data point. Then influence plot. So high influence plot. So this is a leverage. And here also we can see 76 has high leverage. That means this is very far away from the center of this main mass. Okay. Now our target is 76th data point has to be removed along with the 70 also. 70 also here you can see high leverage, right? Now we are going to remove 70th data point, 76th data point from the data set. Right. So then remove the data, the 70th and 76th data point from the data set. So this is what we are doing now. Yes. So we have removed that. After removing these data points, then again, let us build the model. Okay. So after removing those data points and also after removing the WT, right? So the weight, which is the collinearity problem was there, right? So we have removed WT and the data points. Then here we have got the higher accuracy, 0.81. So against 0.77, the AAC value is 446, and with weight, so let us see how much it is. Yeah, 81 and zero point 0.6. So relatively, so the volume is giving us little higher accuracy, 0.8161, and this is 0.8160. Though the difference is very little, but this is there is a little higher here, right? And even the AC values also. So this is a little low than this. That means we'll discard WT and we'll go with volume only. Fine. Then Cook's distance. Once we build the model, again we have to check for the Cook's distance. Are there any data points? So are resurfacing as a outlier. Let us see that now. Yeah. So here one more data point. So that is more than 1.2. So when you remove one data point, one outlier, so that does not guarantee you that so all the outliers are removed, right? So once you remove one outlier, so it is possible that when you build the model and when you again go for the Cook's distance, there might be some other data point that might act as or that might surface as outlier. So that is what actually happened here. So we have removed one data point, again one more data point now appearing as outlier. This also has to be removed. Get the index values of that and remove from the data set. Right. Then I'm removing those data points. Then I have the data set for car 4. Now with this, I'll go ahead and build the model. Then again check. So what is the influential data points? Now, yeah. So here this is the data point. What is the value? This is 0.8 or 0.9, which is less than 1. So if you wish to remove, yes, you can go ahead and remove. Otherwise, you can leave. No, you can stop here. The model deletion diagnostic process, right? Then our model is finalized. Yeah. Yes. So the model is finalized. Now let us find out the R square value. Yeah. So the final model R square value is 0.86. So originally when you build the model, the R square value is 0.77. So after identifying the outliers, after identifying certain problems, so we have increased the R square value from 0.77 to 0.86. That means almost 0.87. Right? Yes. So once the model is finalized, then we'll go for prediction. Now, how do you predict? So imagine that there is a car. So for that car, you want to find out the mileage, right? So then you take the cars, the HP, horsepower, volume, top speed, and then weight. Okay? So just take those values, build a data frame. Then, so this data frame, I'll pass it to the model and call the predict method. Then I'll get the predictions. Yes. Now a car that has 40, a HP 95, volume 102, top speed, right? So that car, the MPG is 46. So that's how we can use. So that is what actually we have seen in the car valley also. The price of the car, when you supply the various input variables values, then the car valley method gave you the price. So here also, when you supply this car's information like this, then you will get the final outcome, that is a predicted value for the MPG, miles per gallon, right? Yeah. So that's how we can build the multiple linear regression equation, and you can validate it, and you can check, you can refine, and you can increase the R square value. Then finally, you can use that for prediction purpose. Okay, right. So this is what I would like to cover for today. Okay, yeah. So we'll stop here for today, and tomorrow we are going to start the data mining topics. So tomorrow we'll discuss about the clustering analysis. Okay, right. And we'll post these the data sets and the Python codes in the Google Drive, including yesterday's also. So you can just check tomorrow and you can practice them. Okay. Okay. So there's one question. Right. So we do not have any branch, okay, in Gurugram. Okay. So we have branches in Mumbai, Pune, Hyderabad, and Bangalore. Yeah. So if you wish to contact, so you can contact any of the branches in these 4 locations. So if you have any questions, we'll happy to help you on that. Right. I see a few problems. Yeah. Attendance. No. So anyway, that will be resolved. Thank you. Yeah, as we understand that, yeah, there are certain problems with attendance link. Please wait. Our team is working on that. Okay, then we'll do one thing. Okay, so we will consider this attendance based on the yesterday's presence as well as tomorrow's presence. So if you had attended yesterday, and then if you attend tomorrow, then we will consider your attendance today also. Yeah, you don't have to worry about this today's attendance. So we had attended yesterday, and if you attend tomorrow, then we'll consider your attendance today also. Fine then. Thank you. If you present tomorrow, yeah, so definitely we'll consider your attendance today. No problem. Yeah, you can leave. You guys can leave. Thank you. Thanks for coming, and we'll meet tomorrow. Thank you. Tim, can you please share our Hyderabad contact details? So it's Learner's Nest. You can leave for the day. You don't have to wait. So we will consider your attendance. Thank you. Yeah, we have got your contact details, Dr. Lubna Siddiqui. So if you need any details, yeah, we'll get back to you. We'll call you. So we have got your contact number with us. Uh, yeah, friends, you don't have to worry about this attendance. So if you have attended yesterday, or if you are going to attend tomorrow, then we'll consider that as an attendance for today also. That's fine. Okay. Thank you. So we are ending this live session. Thank you very much. Bye.